Just let me know if you can't hear me. So this is joint work with Ruben, who's lurking there, his camera off. Oh, first of all, thank you, Simone and Christina, for the chance to talk. It's very nice to finally have a chance to talk here. Yeah, so this is a fairly light work, which is suitable because it's almost Christmas and everyone's tired. So there's no really heavy proofs in here. I just really want to give you an idea of something which I think is algorithmically interesting. And then I will say a little bit about the proofs, but as I say, there's nothing too heavy. More a spin-off from other work we did, but we're very fond of it, so I'm happy to be able to. So, okay, I think you all know this. Trees, leaf labels X. Today I'll only be talking about binary trees, typically unrooted, but in the context of what I'm talking about, the presence or absence of a root doesn't matter. So if you prefer rooted trees, fine, but they're naturally unrooted trees. So let T be a tree on X, unrooted binary tree. So a character F, it's simply a partition of X. Okay, so we really care about the grouping more than the names we give to the state, as it were. And yet the blocks of F, the components of the partition, we call states. And very standard concept in a lot of phylogenetic theory, a character is convex on a tree if the spanning tree is induced by the states, so one spanning tree per state, are vertex disjoint in the tree. So here's a very simple example of a convex character on the tree I showed before. It's got 1, 2, 3, 4, 5 states given by different colors. And you can see that if you take the spanning trees of each block, you end up with vertex disjoint trees. So this is convex. This one is not. So here we have 4 states, this one, this one, this one, this one, and it's not convex because the spanning tree of the red state 1840 and the spanning tree of the blue state 9275, they intersect. So this is not a convex character. So this started a little while ago, some years ago, and we're wondering how many convex characters can there be on a tree? Okay, so this was our starting question. And one of the things we discovered quite early on, and this is work I did with Georgios in my group, leveraging early results by Mike Steele in his ubiquitous 1992 work, was the following result. So if you have an unrooted binary tree on n leaves, the number of convex characters on it is independent of topology of T, and in fact is exactly equal to the 2n minus 1th Fibonacci number. Okay, so there's a closed expression for Fibonacci numbers, and if you plug all the right things in, you end up with this expression as the number of convex characters on an n leaf tree, and then this turns out to be roughly the golden ratio squared to the power n, which is around 2.681 to the n. So that's the number of convex characters on all n leaf trees. But then we were, for reasons which might become clear a bit later, we started asking, okay, convex characters, fine. What about if we restrict the space of convex characters in some way? We wanted to know, what if we want to only count convex characters when each state has at least 2 leaves in it, at least 2 taxa in it. So in other words, you're not allowed singleton states. So let's call the number of such characters G2 of T. And of course, there's nothing specific about 2. You could insist on this a low bound of K per state, and then we have GK of T. So G1 of T is just a set of all unconstrained convex characters. So just to make sure everyone understands what I mean, this is not a valid G2 character. It is convex, but it's not valid G2 because you see here we've got, this guy's only got 1 state, so is this one, and so is this one. Any one of them is a certificate that it's not a G2 character, but here we actually have 3. But this is not a valid G2 character. This one, however, is. Every one of the 4 states has at least 2 leaves in it and is convex. So this is the kind of thing we want to count in G2. So what we proved was, and it was a little bit surprising when we first proved it, the number of G2 convex characters on the tree T with n leaves is also independent of the topology of T, just like for G1. And it's independent and it has a closed expression, and it's the n-1th Fibonacci number. So again, there's a closed expression for Fibonacci numbers. And if you crunch the numbers, you end up with this, which says that G2 on an n vertex binary tree is, yeah, essentially around 5 to the power n, 1.681 to the power n. Okay. And if you want the exact number, indeed, you can evaluate this expression. In the same work, this made us naturally ask, okay, so G1 and G2 are topology independent and have something to do with Fibonacci numbers. What about G3 and higher? And we quickly found some simple examples where you can see that G3 is not topology independent. We found two trees which had different G3 values. So this naturally raised the question, okay, for every k equal to 3 or larger, what's the maximum value that GK can obtain on n leaves as a function of n? And similarly, what's the minimum that GK can obtain as a function of n? And we kind of forgot about this for a while. And as a spin-off of other work that we did, Ruben and I, we realized we knew how to solve this. So what I'm going to tell you about today is this. What did we prove? Well, the first thing is the maximum can be characterized kind of cleanly, because if we have a unrooted caterpillar on n leaves, let's call this cat n, okay? This is the maximum. So the highest that GK can get is the caterpillar, right? And the main result is this. So it says for every n, every number of leaves you want, the maximum value of GK you can get on n taxa is the caterpillar on n taxa. And that maximum grows at exactly alpha to the power n. And what is alpha? Well, alpha is a mystical number, and it's the positive real root of the following polynomial here. So to work out the rate of alpha for a given k, you set this guy to 0, you find the positive real root of that polynomial, and that gives you the rate of growth of the maximum. Okay, so this is the result of a recurrence I'll show you later. So indeed, I'll point out where it comes from in a bit. So the minimum, so it turns out we can cleanly characterize the minimum. So what we proved is that something called a fully k-loaded tree, or any fully k-loaded tree on n taxa, is a minimizer for GK. So they're all minimizers. And if you have such a minimizer, the minimum is given by this mysterious expression, which is another Fibonacci-based expression. And you can see, if you ignore all the boring stuff, this is roughly 5 to the power n over k minus 1. So this is the minimum. Okay. What is a fully k-loaded tree? Yeah, I could go into like really nerdy detail, but what it is essentially is the following. It's when all the taxa in the tree can be partitioned into dependent subtrees. And all dependent subtrees have exactly k minus 1 taxa, except possibly 1. So you're allowed one exception from this. That can have, if it wants, less than k minus 1 taxa. And we'll call this the residue subtree. Okay. So everyone's k minus 1 apart from maybe 1. I'll say more about where this comes from in due course, but because I thought, okay, proof's nice. Let's talk about applications for once, Stephen. So I thought, okay, let's talk about that. Why is this potentially significant? This is why. So at the back of our paper, we've made a little table plotting the minima and the maxima for given values, the first 6 values of k. Okay, so this tells you the rate at which the maximum grows as a function of n, as an exponent of n, and this is the minimum. And unsurprisingly, the first two, G1 and G2, the minima and the maxima are the same because they're topology independent, but you genuinely see that as you go to 3 and higher, there's a gap opening up between the minima and the maxima, okay? And I guess one of the main things I want to say is these numbers, they're dropping fairly quickly towards, 1 point something to the power n. Now, for me, when I see this, I think it's a signal that there's maybe something useful algorithmically here. And why is this potentially useful? Well, another little spin-off result from these old results of Georgios and I was it's not just it's not just like bounding things. We actually know how to exactly count GK given a tree. So you give me a tree, I can tell you in polynomial time what GK is, or the number of GK characters. But I can also list them with kind of polynomial delay. So it's basically the time you spend listing them is the number of characters there are. But also because of the way that it's done by dynamic programming, we can uniformly sample from the space of GK very lightly with very light overheads. Okay. So the simplest way of looking at it is you can just loop through all the GK characters in time, so proportional essentially to the number of them. Okay. And indeed, the nice thing about all this, and it almost goes back to the very clean nature of Fibonacci closed forms, there's no huge hidden constants in any of this. It's all very light. So what we did was we thought, okay, how many of these things can you actually list in reasonable time? So this table, I need some explaining. So let me take this part of the table over here, the caterpillar bit. So caterpillars are the worst case. These are the guys with the most GK characters. And we wanted to know, for a given K, what's the largest number of taxa on a tree for which you can generate all the GK characters in 1 second, 10 seconds, or 100 seconds. So for example, this cell here, this says that if you're willing to wait 100 seconds, you can generate all the G3 characters on a caterpillar of any tree, in fact, because it's the maximizer of up to 47 taxa. Okay, and so on. So that's what this means. And to juxtapose against caterpillars, which are the worst case, we didn't take minimizers, because who cares about minimizers, right? They don't occur maybe in practice, but we took random trees as the kind of counterpose to caterpillars. And probably random trees are somewhere between the maximum and the minimum, probably close to the minimum. Either way, let's see what happens. And you see here the numbers are slightly more favorable. So it's not a big difference, but if you take random trees, typically you can generate all the G3 characters on trees with up to 55 taxa in 100 seconds. Okay? And these numbers get better as GK goes up, simply because there's fewer of them. Okay? Now, it depends on who you ask. I think these are actually kind of encouraging numbers if we're talking about exponential time algorithms. Okay. But yeah, I mean, people are dealing with trees with millions of leaves. It's not so impressive. But anytime we're working with small trees, I'd say this is something that could be useful. So let me give you some examples of how we might use this. So what we noticed is it's quite a lot of NP-hard optimization problems where the optimum solution is not necessarily like a convex character, but you can project it back onto some convex character of, let's say, at least one of the input trees. And the trick being that if that mapping is reversible, a very rapid and quick and dirty algorithmic attack is simply to loop through all the convex characters that can, as long as it contains one of these optimal projected characters, we'll find it eventually. And for each one, we simply try it. Every convex character that's of interest, we map it back to the original solution space. And eventually we'll be guaranteed to find, let's say, the best solution to the original problem. Now, I like this because it means you don't have to think. All you have to do is think of a mapping from your problem into the space of convex characters. And then you've got a rapidly prototyped algorithm. Sure, it's a bit slow, but you don't have to think about algorithm design. And algorithm design is hard. So this is the one of the things I want to say from this talk. So a few quick examples. So here's a question. Don't know whether it's NP-hard or not. So I give you a bunch of trees on the same set of taxa. Can you partition X leaves into size 4 subsets? So that in every tree, the induced quartets are disjoint. I don't know, probably not. It's probably NP-hard. But let's say in the context of the talk, I don't care. Because every one of those solutions, if such a solution exists, it will fall in the space of G4 characters, right? Because every quartet you can think of as a state of a convex character with exactly 4 leaves. And then, yeah, sure, it's a bit silly because G4 contains much more than just things with exactly 4 states. It contains things with at least 4 states. But who cares? It will definitely find such a solution if we do the crunching through it, that space. You simply check each one to see whether it's a valid solution. So in terms of running time, that would immediately guarantee, let's say this table over here, this means your running time will in the worst case be like 1.38 to the power n. Caterpillars are the maximizers, the worst case, and probably in practice somewhere between these two bounds. And if you want to look at numbers, that probably means that in the worst case, you can definitely go up to trees with like, in 100 seconds with trees up to 56 leaves, but probably you can get a bit higher on non-pathological trees. So there you go, an algorithm for free, as it were. And it's so naive in some sense, it's very flexible. So I can just add conditionality to it. I can say, okay, don't just give me disjoint subsets in each tree. I want them all to have the same topology. Or I just want that in one of the trees, the quartets are disjoint, right? They're all allowed. The main thing you need is that there needs to be an anchor point whereby on one of the trees, there is a convex character, which can be used to map back to the original solution. Norbert says that the quartet problem might have a linear time algorithm. Sure, might do, but you're good at algorithms and I'm not. So I believe indeed it might be easy, but it's just my point that I sometimes I don't know and don't care. And I just like to have a quick and dirty algorithm. So second example, this one actually dropped out of another angle of research. Suppose you've got 2 trees on the same set of taxa. Can you find a character that maximizes the difference in parsimony scores of that character? Okay. So various people in this Zoom session have studied this problem. I'm not going to go into details, but one of the nice things about this problem is it has an optimum. I mean, there exists such an optimal character which lies inside G2. Okay, you can always guarantee that the optimizer is some convex character with at least 2 leaves per state. And because it lies inside G2, you can use, basically you're guaranteed to get an algorithm with running time in the worst case, well, let's say exactly 1.618 power n. And that will get you up to about 37 leaves in 100 seconds, just with the naive search strategy. Okay. But maybe that's not so impressive, but one of the nice things that we discovered a little later was, because this is all built on the kind of dynamic programming strategy, the uniform generation of these things can be very powerful. And indeed, of course, uniform sampling can be done on very large trees. And so in a paper that Simona and I worked on, we observed, okay, if you can sample from G2, basically, which you can do very easily on an almost arbitrarily large tree, you get a lower bound on this parsimony distance, and that gives you a lower bound on TBR distance. And it turns out this works extremely well. So you don't need to necessarily list them all. Already sampling from this space might be useful. And now one more example, yeah, okay, find me a maximum agreement forest where every component has at least k taxa. So normally this is not constrained, right? An agreement forest, if you haven't seen it before, it's basically a character that's convex on all the input trees, but they induce the same topology in all the trees. So yeah, this can be just done by going through GK, right? Same kind of argument as before. You can easily liberalize the model indeed, so you don't necessarily need to have the same topology in all trees, etc., etc. As long as there's at least one convex anchor point in one of the trees. And this gives a trivial 2.618 to the power n algorithm, the maximum agreement forest, which until a few years ago was probably the best. We've improved it now with a bit more work, but this was an easy result, so a rapidly prototyped result. Now, the code for doing all this is on my website, and it's been lying there bored for several years, right? that was lying there before we bounded the size of these numbers, but now we know the maxima, and we know indeed the worst case rate of growth of these numbers. So we can indeed add running time guarantees if you indeed download and run this code. So in running time, I'll just give you some sketches of the proofs. They're not so surprising when you see them. They're really very standard kind of induction proofs. The main thing was discovering them in the first place and discovering the actual answers. And then once we sort of guessed correctly, the induction wasn't too hard, but it's technical in places. So here is some of the proofs. First, I want to point out why caterpillars are the worst case for GK. So let's actually count the number on caterpillars, and then I'll argue why it's maximum. Well, it's got a very easy recurrence, because if we have a split A, B, okay, and A has exactly K taxa, it's not so hard to see that if you're counting GK characters, you have to, a state has to consume exactly this A. It can't consume a subset of A, because then it would somehow, you know, it would not be a valid GK character. So you're always going to consume all of A. The only thing to decide is whether the state stops here. Okay, so let's say, so there's two options. It contains A and then stops, or the state grows into B and picks up at least one leaf there. So the first case, when A is when A is a state in itself, we can model this here. All I've shown here is the original tree, but with A cut off. So if you can count GK characters in what's left of the tree, you're counting basically GK characters that consume all of A, but nothing else. And the second situation is indeed when you have a state which has all of A and then at least one of the leaf, and you can count them by just cutting off one leaf from A. So you simply reduce the size of A by 1, and then counting GK characters in this is essentially counting that second type of GK character we mentioned. So GK characters on a graph with a split like this is equal to GK on this plus GK on this. Okay. And then if we apply this, I mean, this applies to all trees, but if you apply it to caterpillars, so here's a caterpillar, you get a very elegant recurrence, simply because when you delete leaves from a caterpillar, you also have a caterpillar, so they're closed under leaf deletion. Okay. So it basically says the GK value of cat n is equal to the GK value of the caterpillar with one leaf deleted plus the GK value with the whole, yeah, when you delete the entire pendant subtree of size k. Now this is what's called homogeneous linear recurrence. Very easy to solve. This is a very standard thing to solve in combinatorics. And if you dig out your favorite combinatorics textbook, it will tell you, sorry, my Zoom thing is decided, yeah. It will tell you that the rate of exponential rate of growth of this is equal to, as I said, the solution to this characteristic polynomial. So this is where our rates of growth come from. Interestingly, I don't know whether there's a well-known closed form for this polynomial. I asked several people and they said it's not obvious that this has a closed form, or at least an easy closed form. So those numbers in the table earlier were all, they were just numerically derived, but yeah. But this doesn't answer the question why they are guaranteed to be minimized, as this counts caterpillars, but it doesn't tell us why they are the largest numbers that drop out. And to prove that, you have to do a little bit more work. So one of the first things that we need to see here is that something called linearization never causes this GK number to decrease. So what is this linearization thing? Suppose we have a three-way split like this, a tripartition, okay? And one of the three subtrees hanging off it has at most k minus 1 taxa. So again, because of the idea that a GK character must have a state that consumes all of this subtree, right?
but it's not enough because every state has to have at least k taxa. So any GK character will eat all of this subtree. Sorry, some state will eat all of this subtree, and then something else. Maybe it takes a bit of A, maybe it takes a bit of B, maybe it takes a bit of both. But the point is, because the state here has to go into this path here, it forbids the possibility of GK characters existing, which have states that have bits of A and bits of B in them, but not C. So it forbids the existence of states that bypass C. Now, given that that bypassing effect is not allowed, you can just as well take this subtree now and basically squeeze it up into this path here, okay, which we do here. So you basically replace C with a caterpillar in between A and B. It doesn't preserve the number of GK characters, but it will certainly not cause it to decrease. It might increase, but we don't mind about that because we're looking for maximization proofs. So this linearization is always safe and always causes is safe indeed for maximization. And of course, instinctively you think, yeah, it's getting it more like a caterpillar. That's indeed, first time you see this, you think, oh, it's obvious. Surely if you keep doing this, you get caterpillars out as the maxima. But it's not quite so easy because there's two cases to the induction. And the induction works on not the number of leaves, but the number of leaves plus the number of cherries. So you need a slightly exotic induction to make things work. The good case goes like this. So you start off with an arbitrary tree T, which minimizes GK. Might not be a caterpillar, that's what it is. If you say, if T has a tripartition like this, and if in addition A and B both have at least 2 leaves, then this linearization effect, is good because the new tree T prime after linearizing will have this relationship to the original tree, right? We already said unconditional of the induction, the original tree is less than or equal to the new tree. The good news is, under these circumstances, the number of cherries drops by at least 1. It only drops by at least 1 because A and B both have at least 2 leaves. If A or B have 1 leaf, then this is not guaranteed. But certainly if A and B both have at least 2 leaves, this kind of linearization will definitely reduce the number of cherries. By induction, that then triggers this relationship, okay? So by induction, GT prime is less than or equal to the caterpillar. And chaining these things together, you get that our original tree is less than or equal to the caterpillar on the same number of leaves. But that's only if this tripartition with these special features actually exists. It doesn't always exist. So there's a second case. So we have the same starting point, an arbitrary minimizer T. And let's suppose now we don't have a tripartition where A and B are at least equal to 2. And then this tree C lies between 2 and k minus 1, but it isn't there. Well, it's a little bit of technical work, but if this holds, you can argue that T has a different type of split. In particular, you can argue that T must have a split DE, where D has size exactly k. It's not difficult, it's just technical. Okay. Now, because we have this split with k on one side and then a bunch of stuff on the other, you can essentially apply this, if you like, this caterpillar recurrence. Because we know then that if you have this perfect k split with k versus other stuff, deleting any leaf x from the d side of the split gives you t minus x, and then you've got the remaining thing, which is t minus d, and we know this recurrence from earlier. So this is just directly plugging in this recurrence. So gk is equal to this, so t minus x plus t minus d. And then in both cases, this and this will both have lower taxa plus cherry numbers. So in both cases, the induction triggers again. Therefore, you can say this term is dominated by the caterpillar on that many leaves. this term is dominated by the caterpillar and that many leaves. And then the summation of these two is equal to the counting you get on a caterpillar with n leaves. So this proves in the other case, you're also dominated by a caterpillar. So this is why the caterpillars are maximizers. Okay. Now, last proofy thing I'll say, what about the minimizers? Yeah. Why are these mystical fully k-loaded trees minimizers for GK? Now, just remind you what they are. A fully k-loaded tree, it's a tree when all the leaves are organized in bunched in pendant subtrees. And all the pendant subtrees have exactly k-1 leaves, except maybe one. You're allowed one exception from this. Okay, and we call this the residue subtree. Because I think they call residues these in number theory, it's the remainder, basically. So here's an example of a fully a fully four-loaded tree. I should say it's not just fully four-loaded, it can be fully other-loaded for other k parameters, but it's certainly four-loaded. Why? So you can see here that you can group the leaves into three pendant subtrees. This guy has three taxa, which he needs to have because we're talking about k-1, remember? So we have three taxa, and then we're allowed one exception. So one subtree is allowed to have fewer than three taxa, and here it is over here. So this is the permitted residue subtree. It doesn't have to exist, but it's allowed to exist, and here it is. But this is fully four-loaded, and so I'm basically saying that this would be a minimizer for G4. That's what I'm saying. How does this all work? Well, if you take a fully k-loaded subtree, you've got this decomposition into pendant subtrees, and you can simply collapse them into single points. And you get a very natural backbone kind of scaffold tree. So you simply collapse this, and this into single leaves, and you get a scaffold. Okay. What you get from this is the following insight. If a tree is fully k-loaded, then the number of GK characters on it is exactly equal to the number of G2 characters on the scaffold. Okay. So why is that? Well, it comes to this idea that a fully four-loaded tree, right? If we're counting G4 characters, we know, because these guys have got 3, and less than 3, a state has to completely consume a subtree, right? It never has the choice of splitting it up. So yeah, this will be completely consumed by a state. So will this, and so will this. So because a state needs to have at least 4 leaves, it can consume all of one pendant subtree, but it also has to consume another to get to its magical count of 4. So in other words, a GK character will have to swallow at least 2 of these pendant subtrees. And because every state in every GK character will swallow at least 2 of these pendant subtrees, when you project that back onto the scaffold, you'll have a state that has at least 2 leaves in it. And vice versa, every time you have a G2 character on the scaffold, you can map it back to a GK character on the original tree. Now that's cute because counting G2 is very easy. G2 is this topology invariant version of the GK, right? Remember, all trees have the same G2 count. So that means that all fully k-loaded trees have the same GK count, because in all cases, you will have a G2 count on the scaffold tree, and that G2 count is utterly invariant on the number of, on the topology of the scaffold, and thus it's invariant on the topology of the original tree. Okay, so all fully k-loaded trees have the same count for GK because of going via G2. And then if you plug in the numbers, you plug in you have to do some messing around because of these K subtrees. But if you get this expression out as the GK count on fully K-loaded trees. It's simply evaluating the G2 expression on this scaffold tree, essentially. So this is where the numbers come out for fully K-loaded trees. But again, this is not a proof that they are the actual optimizers, the minimizers. Proof that they're minimizers is quite actually annoying, but I'll give you a quick sketch of it. Yeah, why is it minimum? Let's find out. So this uses, again, this idea of finding a very nice tripartition of the leaves. So the first thing you do is, so if you take an arbitrary minimizer, we're not going to necessarily say this is a fully K-loaded tree, but we'll prove that there's at least one fully K-loaded tree which is less than or equal to it. The first thing you do is you use a bit of magic and you argue that T must look like this. Okay, so you can apply a transformation to T without increasing the GK value. So it eventually has the following form. You have a subtree B with exactly K1 leaves. You have a subtree C with at most K minus 1 leaves. And then you have some subtree A which has strictly more than 2 K minus 1 leaves. Okay, you can actually use a little bit of violence on the tree to make sure that this guy, yeah, he exists. And this leads to a new recurrence system. And it's the same kind of argument as before. If we look at something like this, we can ask, okay, what is the count of GK characters? Again, focusing our attention on this guy. We know, because he's only got K minus 1 taxa. If we're counting GK characters, some state must eat all of this subtree and take something else because it needs to reach K leaves. Now it has different options. The state can consume B and something from A, but decide to completely forego C. So that you can imagine a state which has got a bit of B and something of A. Okay. And then you can express the number of GK characters by basically taking the product of GK on this part of the tree with the product of GK on this part of the tree. And that gives this term here. And I'm sure Norbert's thinking, oh, GKC, that's 0, isn't it? So why is that term even there? Well, sure, it's 0, and several of the terms in this recurrence are just 1, but I leave it in because I want to use it as a kind of a mask for building a tree in a bit. So yes, some of these terms are redundant, but they are actually more there as placeholders for a recurrence argument that's coming up in a moment. So that is the case when the B state binds left, if you like, but not with C. The second case is when the B state binds with something in C, but nothing with A. And that's this term here. So you take the product of A on one side and B plus C on the other. And slightly less obviously, you have the case when the B state binds left and binds right. And then if you think of it this way, you've got K minus 1 leaves in the state here, at least 1 over here, and at least 1 over here. And you can actually express that as the product of states which only bind left and states that only bind right, which is how you end up with this term here. So this is the states, if you like, that bind left, and these are the states that bind left, right. Now, all these isolated terms have fewer than n leaves. So by induction, we know that all these individual terms are larger than or equal to some minimizer, which is a fully K-loaded tree. So each of these terms is greater than or equal to some fully loaded tree on the same number of leaves. So you can plug those in. So this FL is now this minimum achieved by a fully loaded tree on A plus B taxa. This is the minimum achieved by some fully loaded tree on C taxa, and so on. So we took that equality and turned it into an inequality. And what's left to do is, I mean, this is just an inequality. It doesn't prove the existence of anything, right? To really finish the proof, we'd have to show that there exists some fully k-loaded tree which generates this right-hand side as its own counting equation, okay? Because if some fully k-loaded tree generates exactly these numbers, then we have our proof that this thing, you know, is less than or equal to the original gk on t value. So we have to somehow reverse instantiate this expression here. And this is partly why I left all these terms in, even though some of them zero out. And why is this possible? Well, there's two cases. The easiest case is if you stare at this thing and at least one of A and C is divisible by k minus 1, okay? Just suppose that C is divisible by k minus 1, and what I mean here is it's exactly k minus 1. What you then have is a tree with k minus 1 leaves in here, k minus 1 leaves in here. And in terms of fully k-loadedness, that's fine, right? They're not residues, they're just normal size k minus 1 pendant subtrees. What you then have the freedom to do is to take this and replace it by an arbitrary fully k-loaded tree on the same number of taxa. Okay, that's safe. I mean, that you think, what can go wrong? Well, in the worst case, the fully k-loaded tree you plug in here might have a residue subtree. But that's okay, because this is not a residue, and this is not a residue. So your budget of at most one residue subtree is potentially spent here, but that's fine, because you have no trouble. And symmetrically, if A is divisible by k minus 1, it's fine. You spend your residue on this side of the tree. So in those cases, it's fine, because indeed, there's no problem with introducing through the induction a residue subtree. The nasty case, or nastier case, is when neither this guy nor this guy is divisible by k minus 1. Because then the tempting thing is, the obvious thing is to just plug in the, these equivalently sized fully k-loaded subtrees. But then this will be a residue subtree, and there'll be a residue subtree in here. And the trouble then is the induction has created something with two residue subtrees, and that's not allowed. So what you have to do is some weird manipulation, which involves focusing on this A subtree, and involves very careful analysis of where this anchor point is inside this subtree. Once you've got that under control, you can actually then take this new tree, which has maybe two residue subtrees, and then you apply induction again. You apply this kind of decomposition via the recurrence one more time to kill one of the two residue subtrees. If you do that, this double induction, it eventually works. You eventually get there. And that way you then really have a really existing fully k-loaded tree, which is indeed got a smaller GK count than your original tree via these several steps. So I only have one more slide. So I guess my take-home messages are this convex character programming, right? This quick algorithm prototyping just by looping through or sampling these GK characters. I love this kind of lazy stuff because I like modeling, right? I just think if anyone thinks they could use it, I'd be happy to help out. How do these GK values, how do they vary between the lower and upper bounds? So we know maxima, we know minima. Can you somehow parameterize how these change between these bounds based on a function of tree shape? We know for G3 that as the number of cherries increase, you move further from being a caterpillar and you move further to being a fully loaded tree. But that's only it's a weak bound. If you read the paper, you'll see that it does help to give a smooth upper bound that tends towards the minimum. But for small numbers of cherries, it's weaker than the caterpillar bound. So it's useless for small fractions of cherries. But yeah, there's a whole world of stuff open there. These GK values, did they change much when you apply NNI, SBR, TBR moves? Don't know, not really thought about it. It's probably linked to literature on the way things like parsimony scores behave, but we haven't looked at them. If you're being really nerdy, you can take all the GK values from K from 1 to N, only about half of them are relevant, and simply write them down as a vector. We first conjectured that that vector of GK values would uniquely identify trees, but they don't. They're not easy to find, but we found some examples where you have two non-isomorphic trees that have the same vector of GK values. What does that mean? I have no idea, but if someone's interested in some like math for the sake of math, it might be interesting to understand when do two trees have the same vector of GK values. Moving forward, yeah, are there other natural restrictions on convex characters that could enable more modeling? What you need, I mean, we can model what we want, but what you ultimately need is that there shouldn't be too many of these things. It should be easy to list them, to count them, to sample them. Then you have potentially a powerful tool. I'm doing a little bit of follow-up with Vincent on some of the more natural follow-ups to this, but we only just got started on this. As a general point, I think it's an interesting thing to focus on. And yeah, networks, I don't know, there isn't, as far as I know, one paper on counting convex characters on networks. I can't remember what it means exactly, but that's in Journal of Computational Biology. But you could probably take all the GK stuff and with your favorite definition of what that means on a network, you could probably try and look at all the machinery through the lens of networks. That's it. That's my talk. So thank you for listening. I'll leave it there. Thanks a lot.